We humans are pattern seekers. We look up at the night sky and connect the dots, telling stories of hunters and heroes. We build rules to describe the world, laws of physics that govern the fall of an apple and the waltz of the planets. We take comfort in these rules. They give us a sense of order in a vast and sometimes chaotic cosmos. Science is our most powerful tool for finding these patterns, for reading the universe's instruction manual. Yet, every so often, the universe refuses to cooperate. It presents us with a result that just doesn't fit, a piece of the puzzle that seems to come from a different box entirely. These are the anomalies. They are the beautiful, frustrating, and exhilarating glitches in our understanding. They are not mistakes in our measurements. They are whispers from the cosmos, hinting that our instruction manual is incomplete. They are messages from the frontier of knowledge, telling us there is more to the story. These are the places where the known laws of nature seem to bend, or even break. They challenge our most cherished theories. Imagine a thunderstorm, not just the rain and wind, but the raw electrical power of nature unleashed. You see a flash, and you hear the thunder. But then, something else appears. A glowing sphere of light, perhaps the size of a grapefruit or a beach ball, emerges from the chaos. It doesn't streak across the sky like a normal lightning bolt. Instead, it drifts. It floats silently through the air, hovers for a moment, and then vanishes, sometimes with a pop, sometimes with a fizzing sound. For centuries, reports of these ethereal orbs were dismissed as folklore or optical illusions. But the reports kept coming. Pilots, scientists, and ordinary people from all over the world described the same uncanny phenomenon. The evidence became too consistent to ignore. We now accept that ball lightning is real, but we face a profound puzzle. We have no idea what it is. It defies our simple classifications of electricity and weather. Is it a pocket of superheated plasma, a kind of self-contained thundercloud in miniature? Or is it something more exotic, a chemical reaction ignited by the immense energy of a lightning strike, perhaps involving silicon vaporized from the soil itself? Scientists have tried desperately to bottle this ghost. In laboratories, they zap different materials with high voltages, attempting to recreate the conditions of a thunderstorm. They have managed to create glowing fireballs that last for a second or two, mimicking some of the properties reported by eyewitnesses. These experiments suggest that the chemical theory, where lightning vaporizes elements like silicon to create a glowing cloud of nanoparticles, has some merit. Yet none of these lab-made creations perfectly match the size, longevity, or strange behavior of the real thing. The mystery of ball lightning matters because it reminds us that even our own planet holds secrets. It's a piece of high-energy physics happening right in our backyards. A phenomenon that our current theories of matter and energy cannot fully explain. If we can solve it, we might uncover a new way that energy can store and express itself. A new state of matter hiding in plain sight. Until then, these silent, glowing spheres will continue to drift through our skies as beautiful, unanswered questions from the storm. Now let's leave Earth's atmosphere and journey deep into intergalactic space. Our telescopes are not just eyes, they are also ears, listening for faint whispers from across the cosmos. In 2007, we heard something new. It was a blast of radio waves, incredibly bright, but astonishingly brief. Then it was gone. We call them fast radio bursts, or FRBs. In that tiny fraction of a second, a single FRB can release more energy than our sun does in an entire day. It's a scream from the void. What could possibly generate such an intense, fleeting signal? The bursts come from galaxies. In the 1970s, humanity dispatched two robotic emissaries to the outer solar system, Pioneer 10, Pioneer 11. They were our first explorers to journey past the asteroid belt, to fly by Jupiter, to fly by Saturn, and to venture into the cold, dark expanse beyond the planets. Their mission was a triumph of engineering and exploration. After they completed their primary tasks, they just kept going, coasting out toward interstellar space. And as they coasted, we listened, tracking their faint radio signals to measure their speed and trajectory with incredible precision. That's when we found something strange. Both spacecraft were slowing down. It was an infinitesimal deceleration, a tiny, persistent pull backward toward the sun, about 10 billion times weaker than Earth's gravity. It was as if an invisible anchor was gently tugging on them. This was the Pioneer Anomaly. For decades, it baffled scientists. Our understanding of gravity, codified in Einstein's theory of general relativity, is one of the pillars of modern physics. It predicts the orbits of planets and the bending of starlight with exquisite accuracy. But out here, in the cold depths of space, it seemed to be just a tiny bit off. Was this it? Was this the first hint of new physics? A sign that our theory of gravity needed a modification? The idea was tantalizing. Perhaps gravity behaves differently over vast distances. Or maybe some unknown force was at play. Physicists proposed dozens of exotic theories to explain the anomaly. The stakes were enormous. A deviation from general relativity, no matter how small, would revolutionize our understanding of the universe. The Pioneer probes, long after their official missions had ended, had accidentally become the most profound physics experiment of their time. After years of debate and investigation, a more mundaneo but equally fascinating explanation emerged. A team of scientists went back and reanalyzed everything about the spacecraft themselves. They realized that the probe's nuclear power sources generated heat. This heat had to go somewhere. It radiated away from the spacecraft, mostly from the back of their large antenna dishes. This radiation, this gentle outward flow of photons, acted like a minuscule rocket thruster, pushing the spacecraft ever so slightly forward. From our perspective on Earth, looking at the probes as they receded, this forward push looked exactly like a backward pull, a deceleration. Everything you see, your chair, the air you breathe, the stars in the sky, is made of what we call normal or baryonic matter. Baryons are the family of particles that includes the protons and neutrons that form the atoms of you and me and everything we can touch. Using our theories of the Big Bang, we can calculate with great confidence how much of this normal matter should have been created in the fiery birth of the universe. We can then look at the nearby universe, at the stars' gas and dust in galaxies, and add it all up. Here's the problem. When we do the accounting, the numbers don't match. When we survey the galaxies and galaxy clusters around us, we can only find about half of the baryonic matter that we know must exist. It's a cosmic case of grand larceny. Half of the stuff that should be there is missing. Where did it all go? This isn't like dark matter, which is a completely different kind of substance. This is the ordinary stuff, the protons and neutrons, that has seemingly vanished into thin air. This is the missing baryon problem. Scientists didn't think the matter was truly gone. It had to be hiding somewhere, in a form that was very difficult to detect. The prime suspect was a vast, tenuous network of gas filaments stretching between the galaxies, known as the warm-hot intergalactic medium, or WIM. Imagine, unimaginably huge clouds of gas, millions of light years long but so thin and diffuse that they are almost perfectly transparent. This gas would be heated to millions of degrees, but because there are so few atoms, it wouldn't shine brightly enough for our telescopes to easily see. Finding this hidden matter required a clever strategy. Astronomers used powerful sources of light from the distant universe, like quasars, as cosmic flashlights. As the light from a quasar travels across billions of light years to reach us, it passes through these invisible filaments of gas. Certain atoms in the gas, like oxygen, absorb very specific colors of X-ray light. By looking for these tiny specific gaps in the spectrum of the quasar's light, we can detect the presence of the hot gas. It's like seeing the shadow of a nearly invisible object. And in recent years, using sensitive X-ray space telescopes, let's venture to the edge of a spiral galaxy, much like our own Milky Way. From here, we can watch the stars orbit the galactic center. Isaac Newton's laws of gravity predict orbital speeds drop with distance. Stars on the outskirts should be crawling, but observations surprised astronomers. Outer stars moved as fast as inner stars. This makes no sense. Visible stars alone, gas, dust, couldn't produce enough gravity. Galaxies should have flown apart. So there must be extra mass, completely invisible. It doesn't shine. It doesn't reflect light. It only interacts via gravity. We call it dark matter. Evidence multiplies. Galaxy rotation, cluster motions, gravitational lensing. The conclusion: about 85% of all matter is dark matter. Ordinary matter, you, me, and all visible stars, is a tiny fraction. What is dark matter? Not dim stars, not uncounted black holes. Leading idea: a new subatomic particle outside the standard model. Names: WIMPs, weakly interacting massive particles. Axions, experiments worldwide are searching. Detectors deep underground, shielded from cosmic rays, waiting for the 1 in a trillion chance that a dark matter particle will bump into one of their atoms. Finding it would be one of the greatest discoveries in the history of science. Let's travel back in time, all the way back. Back to just a few minutes after the Big Bang. The universe was an incredibly hot, dense soup of elementary particles and radiation. As it expanded and cooled, protons and neutrons began to stick together to form the first atomic nuclei. This process, called Big Bang nucleosynthesis, was the universe's first act of cosmic alchemy. Our theories of cosmology and particle physics allow us to calculate, with stunning precision, how much of each of the lightest elements should have been forged. Our calculations predict a specific amount of hydrogen, helium, and a tiny trace of lithium. When we look out at the oldest stars in the universe, pristine fossils from that early era, we can measure the elements they contain. For hydrogen and deuterium, the measurements match the predictions perfectly. It's a spectacular confirmation of the Big Bang theory. But when we get to lithium, the story falls apart. The oldest stars have only about 1/3 of the lithium that our theory says they should have. This glaring discrepancy is known as the cosmological lithium problem. Where did the lithium go? Or was it ever there to begin with? It was a simple question with two possible answers. If there was enough matter in the universe, gravity would eventually win, and the expansion would slow, stop, and reverse in a big crunch. If there wasn't enough matter, the expansion would slow down but never quite stop, and the universe would expand forever, growing colder and darker. The only question was which future awaited us. In the late 1990s, two teams of astronomers set out to answer this question. They used distant exploding stars, supernovae, as standard candles to measure the expansion rate of the universe over cosmic time. They expected to find that the expansion was slowing down. What they found was the exact opposite. The expansion of the universe is speeding up. Something is pushing space-time apart, acting as a kind of anti-gravity on the largest scales. The universe is not just expanding, it's accelerating. This was a discovery that shook the foundations of cosmology and earned a Nobel Prize. We have a name for the cause of this acceleration: dark energy. But naming it is not the same as understanding it. Dark energy is the biggest mystery in all of science. When we do the math, we find that this strange energy makes up nearly 70% of the entire energy density of the cosmos. It is the dominant component of the universe, and we have absolutely no idea what it is. Is it a fundamental property of space itself, an energy of the vacuum that Einstein once proposed and called his biggest blunder? Or is it a new dynamic energy field that permeates all of space, something that might change over time? The most terrifying possibility is that our theory of gravity is wrong. Perhaps on the scale of the entire cosmos, gravity doesn't just pull, but can also push. Answering this question is the single most important goal in cosmology today. Huge new observatories, both on the ground and in space, are being designed to map the universe in unprecedented detail. By precisely measuring the positions and distances of hundreds of millions of galaxies, they will trace the history of cosmic expansion. This will allow us to test whether dark energy has been constant or if it has changed over time. The answer will determine the ultimate fate of everything, and it could unveil a new law of nature. So there they are, 7 dispatches from the frontiers of science. From ghostly lights in our own atmosphere to the very fabric of space-time being stretched apart, these mysteries are not signs of science's failure. They are the exact opposite. They are the markers of its progress, the growing pains of our understanding, An anomaly is simply where the next great discovery is waiting to be made. Every revolutionary idea in history, from the Earth revolving around the sun to the bizarre rules of quantum mechanics,